In this presentation, we focus on a compliance-critical reality in container terminals. Refrigerated containers must be monitored on a strict schedule to protect temperature-sensitive cargo. When monitoring is manual, the operation becomes slower, riskier, and more error-prone. The goal is to design a repeatable inspection plan that keeps inspections on time, reduces safety exposure, and protects high-value cargo from preventable loss. The problem is a practical scheduling challenge. You must decide which inspector checks which reefer, in what order, and at what times, while also documenting every inspection for compliance. The main operational drivers are the mandatory inspection interval, the safety risk created by stacked or remote containers, and the high penalty of lateness when the cargo is high value. This deck is grounded in a realistic terminal setting. At the Port of Valencia's container terminal, Supervisor Maria Rodriguez manages reefer monitoring across 2,400 refrigerated containers with a team of 18 inspectors. Mandatory temperature checks must occur every 4 hours around the clock, and stricter European Union regulations require detailed documentation such as timestamp, container identification, readings, alarm status, and inspector identification. Tier 1 builds the baseline model. We treat reefer monitoring as a multi-objective assignment and routing problem with time windows and priority constraints. The key reason to model this formally is to make the trade-offs explicit. You must balance inspection time, safety risk, and lateness penalties in a way that can be audited. The variables represent concrete yard decisions. One set of decisions assigns each container to an inspector. Another set of decisions represents the visit sequence, which forms the route skeleton for each inspector. We also track start times and a lateness quantity, which captures how late an inspection occurs relative to the required interval. This prevents a failure mode where a schedule looks efficient, but hides compliance violations. The model begins with the set of reefers that require inspection and the set of inspectors available. Parameters include inspection times that depend on accessibility and experience, inspector capacity per shift, and the maximum allowable time between checks. Priority weights represent cargo sensitivity and value. High-value pharmaceutical containers receive the highest weight. Standard food products receive a medium weight, and less critical cargo receives a low weight. The core decision is assignment. Every reefer must be mapped to exactly one inspector. We also represent route order by indicating which container is visited immediately before another. Finally, we include start time decisions and lateness tracking. Lateness exists because travel time, congestion, and safety protocols make the yard dynamic, not a static checklist. The objective function is a weighted combination of 3 costs. First, total inspection time. Second, safety risk exposure based on how difficult and dangerous access is for a given inspector and container. Third, a cargo protection penalty that grows when high-priority containers are inspected late. Operationally, the objective prevents a common failure mode, optimizing only for speed while shifting risk onto inspectors or allowing high-value containers to go uninspected past the required interval. The assignment constraint enforces complete coverage. Every reefer must be assigned to exactly one inspector. This prevents 2 failures: missing containers entirely and duplicating effort by scheduling 2 inspectors for the same container. Inspectors have finite capacity within a shift. Capacity can be interpreted as the available work time budget, including travel and inspection activity. This constraint prevents the schedule from becoming optimal on paper but impossible in reality, such as overloading one inspector while leaving others idle. The time window constraint captures the mandatory inspection interval. Each container's inspection must occur within the maximum allowable time between checks. This is the compliance backbone. It prevents the failure mode where low-risk travel savings cause a high-priority container to be checked too late. The visualization shows the yard layout, safety zones, and the way routes emerge when you assign inspectors to containers. Some areas are higher risk, especially where containers are stacked high. Use this slide to connect math to reality. The solution is not only who is assigned to what, but how much walking is required and where safety exposure is concentrated. Consider the 6-container, 2-inspector example. The example includes pharmaceutical, food product, and general cargo reefers with different accessibility levels that change inspection time. The optimal assignment sends ground-level, safer inspections to one inspector and assigns stacked, higher-risk checks to the more experienced inspector. This improves safety and reduces the chance of late checks for high-priority containers. Tier 2 introduces a deployable heuristic, a priority-based greedy assignment rule driven by a composite score. This is designed for real-time operations when you cannot solve a full model repeatedly. The heuristic is particularly useful when conditions change during the shift, such as alarms, congestion, or sudden weather constraints. The scoring function ranks candidate assignments, meaning a specific container paired with a specific inspector. The score includes cargo priority, inspection urgency, safety and access difficulty, and workload balance. This scoring definition is the heart of the heuristic because it determines what the greedy method will consistently prefer. The composite score is a weighted blend of multiple factors, so it can represent terminal priorities. For example, if compliance risk dominates, urgency and lateness risk should carry a heavier weight. In practical terms, the composite score answers which inspection should happen next, by which inspector, to protect high-value cargo without increasing unsafe exposure. The flow is an iterative loop. Evaluate all feasible container and inspector pairs, select the best scoring assignment, update the inspector route state, and repeat. This structure is simple enough to run frequently, and it produces decisions that supervisors can audit and explain. This code part defines the container and inspector representations, along with the state variables needed to compute scores. It also establishes the concept of current time, because urgency depends on time since last inspection relative to the required interval. This section computes scores for each container and inspector pairing, combining urgency, safety, and workload balance. The key operational point is that the same container can be a good choice for one inspector and a poor choice for another depending on location, capability, and current workload. This part commits the best assignment and updates the schedule state. Once an inspector is assigned a container, their remaining capacity and current location change. The algorithm then recomputes scores using the new state, which is how it stays responsive rather than behaving like a one-time sorting. This part typically applies a small local improvement step, such as to-opt, to reduce unnecessary travel within an inspector route. The aim is to keep computation light while still fixing obvious path inefficiencies that greedy assignment often creates. The sample output shows the schedule per inspector as a route sequence with container metadata. For example, you can see that high-priority pharmaceutical containers are scheduled early. This is operationally useful because it makes the plan inspectable. A supervisor can immediately confirm that high-risk stacked containers are assigned to qualified inspectors. The second part summarizes performance. Total time per inspector, safety score, achieved average inspection interval, and workload balance. These metrics matter because speed alone is not the objective. The yard needs schedules that are safe, balanced, and compliant. The greedy method repeatedly evaluates container and inspector pairs. In plain terms, the core assignment step grows roughly quadratically with the number of containers and also scales with the number of inspectors. The optional route cleanup step, such as to-opt per inspector, improves travel but can add extra compute. The strength is speed and explainability. The weakness is the risk of getting stuck in a locally good but globally poor plan. Tier 3 uses simulated annealing to escape local optima. Instead of always accepting only improvements, the algorithm sometimes accepts worse moves early on, in a controlled way. This helps discover better global schedules, especially when constraints and priorities conflict and you need coordinated changes across multiple inspector routes. The energy, or cost, is the composite objective you want to minimize. Total time, safety penalties, workload imbalance, and compliance violations. Defining this cost correctly is essential. If you do not penalize late inspections for high-priority containers, the search will optimize travel and accidentally create compliance risk. The acceptance rule can be explained simply. If a move improves the schedule, accept it. If it makes the schedule worse, accept it with a probability that depends on how much worse it is in the current temperature. High temperature means more exploration. Low temperature means stricter improvement and convergence. Temperature is the control knob for exploration versus exploitation. Early, the algorithm explores more aggressively to avoid premature convergence. Later, as temperature drops, the algorithm becomes conservative and stabilizes on a schedule that balances time, safety, and compliance. This code section defines schedule representation and neighborhood moves, such as swapping two tasks, relocating a container to a different inspector, or reversing a route segment. The neighborhood defines what the algorithm can explore. If the neighborhood is too limited, the algorithm cannot reach high-quality schedules. This section evaluates a neighbor move by measuring how it changes the composite cost, including time, safety, and lateness penalties. Accuracy matters. If cost evaluation is inconsistent, the algorithm will chase noise instead of true improvements. This section applies the acceptance rule, updates the temperature schedule, and tracks the best schedule found so far. Even if the current schedule temporarily worsens during exploration, the algorithm preserves the best plan so the final output is stable. These results show an optimized schedule produced by simulated annealing. Compared to greedy, the schedule typically reduces travel and improves compliance under the same capacity. The improvement comes from coordinated route changes that greedy selection would not consider. This continuation summarizes outcomes such as reduced lateness, improved workload balance, and safer assignment patterns. The important point is that the method improves trade-offs, not just a single metric. Expected improvements compared to greedy include better global routing, improved workload balance, and more reliable handling of constraints through explicit penalties. The trade-off is computation time and parameter tuning, but it remains operationally feasible for planning runs and periodic schedule refreshes. Tier 4 models inspection scheduling as a Markov decision process and trains a deep queue network agent to make sequential assignment decisions. The advantage is adaptation. As conditions change, the agent can learn policies that remain effective without manually retuning the heuristic weights. Terminal conditions change continuously. New arrivals and alarms, equipment availability, weather changes, and inspector fatigue and shifting workloads. Reinforcement learning helps because the decision pattern repeats every shift. With enough experience, a learned policy can respond quickly without rebuilding schedules from scratch. The state summarizes what matters now: time since last inspection, container priority, inspector availability and location, and environmental conditions. The action assigns an inspector to a container at a chosen time. The reward penalizes lateness, inefficiency, and unsafe actions, and rewards compliance and balanced workload. A deep queue network updates action values by combining immediate reward with the expected future value of the next state. A separate target network improves stability by keeping the learning target from changing too rapidly. The network takes the state representation as input and outputs a value estimate for each feasible action option. Feature design is critical. If the state does not encode lateness risk or access risk, the policy cannot learn to avoid failures. The architecture must balance expressive power with stability, so it learns patterns without becoming brittle. This code section defines the environment and the state encoding for the agent. It converts operational reality into model inputs such as time since last inspection, travel distance, priority weight, and access difficulty. This section defines the deep queue network and the action selection policy. The agent balances exploration and exploitation. It tries new choices early in training and uses learned choices more often later. This code part implements experience replay, storing transitions and learning from randomized batches. Experience replay improves stability and reduces the chance the agent overfits to short-term correlations. This section implements the training step in periodic target network updates. The purpose is to prevent unstable oscillations during learning. This part includes evaluation metrics such as compliance rate, average lateness, total travel, and safety distribution. These metrics ensure the agent is improving operational outcomes rather than optimizing an unintended proxy. This final code section typically includes checkpointing and deployment hooks. In real operations, monitoring and auditing are essential so a learning system remains safe and predictable. Training results typically show improved compliance and reduced lateness compared to non-learning baselines. In this problem context, learning is especially important because bad weather can double inspection time under safety protocols, and the schedule must adapt without violating the 4-hour requirement. This continuation highlights qualitative behavior. For example, the agent may postpone low-risk tasks during adverse weather and then catch up later or rebalance workload proactively before bottlenecks appear. The key takeaway is adaptive decision-making under uncertainty while staying compliant. Tier 1 provides the exact structure and a correctness baseline. Tier 2 provides a very fast and explainable operational rule. Tier 3 improves quality through search, and Tier 4 learns an adaptive policy that can respond to changing conditions. The practice questions ask you to translate the ideas into implementable work. You practice writing a complete model, implementing the greedy heuristic, and designing neighborhoods and cooling schedules for simulated annealing. You also practice defining the reinforcement learning elements, state, action, and reward in plain English. Manual reefer monitoring is compliance critical and safety sensitive, and failures are costly. In this scenario, a malfunctioning reefer went undetected for 12 hours, and a pharmaceutical shipment worth $2.8 million was lost. A tiered toolkit is practical. Start with a complete baseline model, deploy a fast heuristic, use simulated annealing when you need better global schedules, and use reinforcement learning when the environment is dynamic and decisions repeat.